If you've ever heard the word calculus and immediately thought of some scary, impossible math class, I want you to just take a breath and forget all of that. Because today, we're going to see it for what it really is. It's a language, a powerful, kind of beautiful language that was invented to describe a world that is always, always in motion. So you ready? Let's dive in. Everything around us is changing, but how do we talk about that change with any real precision? I mean, think about a swimmer in the middle of a race. Her speedometer, if she had one, might flash a speed. That's not her average speed for the whole lap, right? It's her speed at that exact moment. But hold on, how is that even possible? An instant has no time. It's 0 seconds long. So how can anything change in 0 time? This is the fundamental puzzle that calculus was born to solve. So to get around this whole 0 time problem, mathematicians came up with this really clever workaround. It's called the limit. The big idea is, instead of trying to look at a single instant, which we can't do, we just sneak up on it. We get closer and closer and closer from both sides and see what the trend is. It's like having a mathematical zoom lens that lets us get infinitely close to the action. And that word right there, approaches, is everything. A limit isn't about what's actually happening at the point. It's about the journey towards the point. As we get ridiculously infinitesimally close, what value is the function zeroing in on? That's the limit. This graph here is the perfect example. So look at where x equals 1. See that little hole in the line? The function's actual value at that point is that lonely dot way down at y equals 3. But for the limit, we honestly don't care about that dot. We only care about the path. As we come in from the left side, the line is heading towards a y value of 4. As we come in from the right, hey, it's also heading towards 4. Since both roads lead to the same place, we say the limit is 4. Okay, so that's all well and good when the path is nice and connected. But what happens when it's broken? What if the journey from the left takes you to a completely different place than the journey from the right? This is what we call a jump discontinuity. Just look at graph B. If you follow the curve towards that point C from the left, you end up down at that lower open circle. But if you come in it from the right side, you land way up at the higher filled-in circle. Since the left and right paths don't meet up, the overall limit at point C just doesn't exist. The function literally jumps from one value to another. Now compare that to graph C. This is different. Here, the paths from the left and the right do agree, see? They're both heading for that exact same open circle. This means the limit exists. The only weird thing is that the actual function value is defined as that other dot somewhere else. We call this a removable discontinuity because, you could totally fix this graph just by moving that one dot to plug the hole. All right, so we have this powerful idea of a limit, this tool for getting infinitely close to a point. But why does it matter so much? Well, it matters because it is the absolute key that unlocks the single most important concept in all of differential calculus, the derivative. And there it is. This is it. This is the answer to that question from the very beginning. The derivative is the instantaneous rate of change. Now, don't let the formula scare you. That fraction part is just the good old rise over run slope formula between 2 points. The lim part in the front is where the calculus magic happens. We're taking the limit as the distance between those 2 points, h, shrinks all the way down to 0. And when it does, the slope between 2 points becomes the slope at one single precise point. So here's the bottom line. For a derivative to even exist, to have a clear, single slope at a point, the function has to be smooth and unbroken right there. You can't find the slope at a spot where there's a big gap or a jump. In other words, being differentiable is a much stricter club to get into than just being continuous. And this graph shows us 2 classic ways a derivative can fail. First, look at x equals -3. We've got a discontinuity, a clear break. You can't find a slope at a point that isn't even part of a continuous line. Then, check out x equals 1. Now the function is continuous there, but it comes to this super sharp point, kind of like a mountain peak. We call it a cusp. The slope coming from the left is negative, but the slope from the right is positive. Since there's no single agreed upon slope right at that tip, the derivative doesn't exist there either. Now, you can imagine that using that whole limit definition every single time you want to find a slope would get old fast. Thankfully, over the centuries, mathematicians developed a whole toolkit of rules and shortcuts to find derivatives much, much more quickly. Let's just glance at a few of the big ones. So here are some of the greatest hits. The derivative of any constant number is just 0, which makes total sense, right? A flat horizontal line has a slope of 0 because it's not changing. The power rule is the absolute workhorse of calculus. And then you get these really cool special functions, like e to the x. Its derivative is itself. The value of the function at any point is literally equal to its rate of change at that same point. How wild is that? Now, rules like the quotient rule can look super intimidating as a formula, but really, it's just a recipe. Think of it like baking a cake. A lot of people even use a little rhyme to remember it. Low d high, less high d low, over the square of what's below. It's just a procedure that helps us tackle the derivative of any messy fraction. Okay, so we've got the theory, we've got the tools. What's the big payoff? Well, the payoff is that we can now model and solve real-world problems where a bunch of different things are all changing at the same time. So check this out. We've got a right triangle. The bottom leg, x, is getting longer by 3 feet every second. At the same time, the vertical leg, y, is shrinking by 2 feet per second. The question is, how is the hypotenuse, z, changing at the exact moment when x is 7 feet long and y is 1 foot long? This is a classic related rates problem. And what's so cool is that calculus gives us a clear, step-by-step game plan to solve it. First, we list what we know and what we need to find. Then we find an equation that connects all our pieces. In this case, it's the good old Pythagorean theorem. And then, this is the key step. We take the derivative of the whole equation with respect to time. That brings all those rates of change into the picture. After that, it's basically just algebra. And after we plug in all our numbers, we get the answer. Even though one side is shrinking, the other side is growing fast enough that at this precise instant, the hypotenuse is getting longer at a rate of 19/50ths of a foot per second. Calculus allowed us to peer into a single moment in time and find a precise answer. That is the power of the derivative. So, if there's one thing you take away from all this, let it be this idea right here. The derivative isn't just some abstract formula to memorize for a test. It is the mathematical tool we invented to speak the language of instantaneous change. It's how we describe the speed of a swimmer, the dynamics of a changing economy, or the slope of a curve at one single solitary point. So we've just seen how to find a swimmer's exact speed at any given instant during a race. But what if we wanted to know the total distance they traveled? What if we could take every single one of those instantaneous speeds from every single moment in the race and add them all up? Well, that process of adding up an infinite number of tiny pieces to get the big picture, that's the entire other half of calculus. And that, my friends, is a story for another time.